Okay, so here's where we continue on with the example from the previous video, and I'm gonna demonstrate making the Excel spreadsheet, and then use this to find do other types of problems, right? So this was the type 1 problem where we're looking to try to find the pressure loss, and then also and from that get what the required pump head had to be. So here is sort of this is what I meant the thing to look like, the Excel formatting, but I changed it ever so slightly for some reason. So I'm going to modify the one that I gave you as the template as part of this. But here's what we want to turn this thing into to be able to do our problem, or something very similar to it. So here we go. Without further ado, let's take a look. All right, so here is the template that I've provided you. And we'll start putting in some of these values right here. So let me go to this right here and shut it down. And we will just copy this over here so we could look through what it is that we wanted to do. Let's see, I'm going to crop this out so I can see it a little bit better. All right, so there's a little bit of a difference coming on here between here. But anyway, we're going to start out with 60. I'm going to go ahead and my later one I got rid of this velocity, but it's not going to hurt us to put that velocity in there. But most often it's going to be 0 for us. But we'll make it so that it's possible to put in an inlet velocity if we happen to know it. All right, so we're going to have to go 0, and we're going to go up to 30 feet, and we're going to make this to 120 psi. And make that 0, and make this 0, because that's the datum. We said we had 120 feet worth of length of pipe. Our diameter of the pipe was, we were given it, we decided to use inches right here. So this is where I have to change my spreadsheet ever so slightly. And I decided to insert a row down here, move this down, and so that I could insert something right in here. So I'll insert. Actually, I could just copy it down. I could just move it down one. Boom. And so I'll set this equal to 0. But whoop, I meant to do it the other way around. Okay. So anyway, I'll just move this up here. Boom. All right. It's okay. So I'm gonna match what I have here on the spreadsheet, but then remember that we actually used the correct inside diameter in the previous video. Here we will just, let's see, won't let me do this. Equals, why won't it let me do that? Something's going on here with my Excel. It's being weird. Okay, there it is. It wouldn't let me enter. What did I do? Oh, jeez. Okay, let me try it again. Why is it acting so weird? All right, need to pause. Okay, it's coming back now. So I have equals there divided by 12. I get in feet. This was an input 0.00015, I believe, is what I need right there, right? Let's take a look back in there. Yep. 1.94 is the density we're using, and we had 2.34 E minus 5 is our viscosity. All right, so the rest of these can be, so some of these can be, not rest, okay. We will find the area, and I want to use feet for the area, squared right there, so that's, let me make this a little bit bigger so I can double check I have, yep. And then divide epsilon by the diameter, make sure they're both in feet, yep. And we take the length and divide it by the diameter. And then I'm going to link over to this, whoops, I want to get rid of that, whoops, get over here, yeah. Link over to that cell right there. So I'm going to hit equals and then go to that, right? Let's enter in all of the fittings. So this is the fittings. Let's see. Boom. So we had one entrance, and we could change this KL, by the way. It's just there for convenience. We don't have to put the zeros into place. We have 2 threaded 90s. We have 1 threaded branch. We have 1 check valve. I forgot 2 globe valves. And we had 1 exit. So we get the 28.8. So we could really kind of get rid of this guy right here. All right, so down here, I'm going to make this the input for right now. We might in other versions of the spreadsheet, we're going to modify this somewhat. And if you look at the old video, you can see what I do is I make an increment. I put like a range in here, and then I make it incrementally by 5%. But for right now, I just want to concentrate on this spot right here. So we're going to take this and divide it by 7.48, which is the number of gallons per cubic foot, and then divide it by 60 so that we get cubic feet per second. Boom. And I'll extend that out there. We can see we got the same thing by hand. We'll find the velocity by dividing that cubic feet by the cubic feet per second by the area. Now I'm going to use the F4 button to put dollar signs next to those, because when we go to copy this cell, we always want to be referring back to that area. So right there's our, we'll give it another 2 sig figs in there. So now we could use that to find the Reynolds number. So take the velocity and multiply that by, let's go by the diameter. We need F4 for that as well. And multiply that by the density. That too needs an F4. And then divide it by the viscosity, which lastly needs an F4. And we should get 67,000, right? So that's just the velocity times the diameter times the density divided by the viscosity, and that's your Reynolds number. Here is a one where it's going to be a relatively long equation. So I'm going to cheat a little bit, somewhat. You can do this yourself, but you can see that here is the write-out that all I'm going to have, and it's an if statement, so that in case the thing is laminar, it will also be useful. But this is the equation that we used over, let's see, here. Nope, right there. Oh, no, where'd you go? Right there. Here's this equation. I believe it's the Halland equation, Halland or OND, something like that. But I have it written, not with the 1 over the square root of the thing. So where did we go here? Right here. So I'm copying and pasting this. I think it's now resolved so we don't have to worry about that minus sign nonsense with the M and the N. But just be aware there might be a problem. But I can go ahead and stick it down in here. But I do have to be careful. So I'm going to come back up into my field right up here and hit Control V after having hit Control C and copying it. One thing of note is that some things shifted because I added a line, right? So I added a line, so it went up. I need to pull this down right there, okay, to get to the E over D ratio. And I think if I hit Enter, I should get, and you can see that I got pretty close to what I got by hand in the last video. We're gonna update that. This is actually for 2 inches for right now. We're gonna update that ever so slightly to measure. All right. So for the head loss, we're going to have, it's going to be in 2 parts. So we're going to go ahead and put an open parentheses and take this F and multiply it by the length. Make sure that you hit your F4 there and divide by the diameter, hitting the F4, right? And they're going to add it to the KL total, hitting F4, and closing the parentheses, multiply it by the velocity, boom, and that doesn't need an F4 because that's gonna change with every row that we use. And we square it, and we divide it by 2, and we divide it by 32.2. And hopefully we got about the same thing as we have in our example, which I deleted. So let me come back up to this. So yeah, 16.8 is what we can expect to have. 16.8, I think we're gonna get another sig fig in there. So now for the HS, I'm going to do slightly different from what the instructions say right here in this. We are going to take this equation right here, but we're also going to add in the velocity. Because we put it in, we might as well include it, right? So let me go like right there, and we're going to be writing in equals parentheses P2 minus P1. Close parentheses, multiply that by 144, and then divide it by density. Oh, by the way, I made a mistake here. Should have gone F4s on both of these. F4, F4, and then F4 right there. And then also divide it by 32.2. So what I did there is I divided it by the, the specific weight, because it's just density and gravity. We're also going to add in velocity 2 and square it. Well, I did it again. Make sure you put the F4s in there. Minus velocity 1, F4, I remember that time, squared. And let's see, yeah, divide by 2. And divide by 32.2, right? So we have that into Bernoulli 2, and then we're going to add V2, excuse me, Z2, and then we're going to subtract out Z1, and we did F4 on both of those, right? And then lastly, we're going to add in the head loss. Now I can't because of where this thing's positioned, so I'm going to pick the one below it and then go up. And for whatever reason, I might have messed something up here. Let's hit at 125.1. Did I get the right thing? Let's double check. Let's see what it said. 125.1. Yes, excellent. Okay, cool. And so we're on the right track, so we're almost there with our spreadsheet. And all we have to do now is make this into power. So we're going to multiply that by our flow rate and multiply that by the density. But we need an F4 right there. And then multiply that by 32.2. And that should give me 836. No, I don't have it down there. All right, so for whatever reason. So we're going to take over here, and we're going to take this and divide it by 550. And sure enough, that is the answer that we expect. But to correspond with the previous video, come up to this and make it 2.067. Where'd you go? Yeah, 67. Yeah, sure. Boom. And you could see the values here. We got 1.493. So we got them to agree. So once we made this thing, I'm going to make sure we save it. And maybe we could go like F22 class. What is today? It was the class 23, or actually class 22, example 2, right? I'm just giving it a name. You can name it whatever you want. But let's copy the thing and see what the power of having done this is. Okay, I'll move this over to the side. and I don't know, I call that example 3. Let's say that we have a flow, and I think I use in class something like 1500. Boom. I might make this back to 2, so it'll be similar to what we did in class. But you can see how huge the power was. And I said what I wanted to do was to use goal seek from the data and the what if analysis right there. And I want to change this. No, I think I made a. Oh, wait. What did I do first? I guess I decided instead. I want 48. I decided I wanted to make. I'm trying to remember which way I did it because this was actually problem 3 that I did, and I can't remember what I had done for problem 3. Or problem 2, I mean. I think I might have said, I want to find out how much flow 100 horsepower would make. Yeah, let's figure out how much flow 100 horsepower would make. So I set this cell to 100 and change that cell right there. So I could find out. So this is the problem 2 part. This is the type 2 problem where I'm looking for flow. And I go here and I find that I would get, whoops, I hit the cancel instead of accept button. So do it again. Change that to 100 by changing that. So the answer is 371 is how much flow would be produced if you had 100 horsepower. Now I also did, so this, we could save that if we want to, right? And moving on to here, we will say maybe this is example 4, we could call it, and do another what if analysis and say, okay, let me start out by here. Let's say that we have established that we have 1,500 gallons per minute, and that power is way too high. So we want to change what the diameter is, which is this is a design problem. So we go back to the goal seek, and we say we want to let's get to 100 horsepower. Maybe that's how big our motor is. So we'll change that by now changing the diameter. And you can see that we're up to about 6 inches. So a 6-inch pipe could do the 1,500 gallons per minute at 100 horsepower of hydraulic power. So there you go. There's the power of using an Excel spreadsheet to solve the piping drop calculation. And now that we have this set up, we could use this for all kinds of other applications, not all kinds of other applications, but several others, and we'll continue to use it. So it's really important as part of your homework that you get this thing working just right so that we can do like pump matching stuff, and it's going to be very useful. So there you go, the end.